Hello, James Flaten here with the Minnesota Space Grant to talk about data analysis of data that's been collected from a high-power rocket flight. Consider this fairly basic analysis. So I'll assume you have a rocket that carried perhaps a data logger like an altimeter 2, which gave you the peak altitude, the peak velocity, the things like that. But then also that you had some sort of an altimeter that fired ejection charges and also logged data, and perhaps even a separate data logging system like a paddle that had sensor data and recorded it as a function of time. So basic data analysis in some sense is trying to see if you can find the features that were logged and recorded by the altimeter 2 in the record, which is as a function of time, especially when you graph the data. So let's take a look at some altimeter 2 records. Okay, so this is from an actual flight. So this particular set of data says that the apogee, the peak altitude, was 3,729 feet, so just over 3,700 feet above ground level. The top speed was just a few miles per hour shy of 500 miles an hour. The burn time was 1.6 seconds. The peak acceleration was almost 17 Gs. The average acceleration was about 14 Gs. The coast time after burnout to reach apogee was just over 12 seconds. The ejection was perhaps about 0.6 seconds later than apogee. The ejection altitude is almost the same as the apogee because it did go off very close to apogee. The descent speed seems high, 44 feet per second, but that might actually be an average between a fairly fast descent under drogue and then a slower descent under main. Maybe we'll figure that out when we take a look at some graphs with a flight duration of just under 100 seconds. So with these numbers in mind, let's go and take a look at the data record that came from an AIM USB. So here's an AIM USB in .csv format. The very first thing I would do is I would save this in genuine Excel format. I'm going to use Excel for this analysis. So let me save as, and I'm just going to rename this. First of all, I'll say that I want it to be an Excel format, and I'll say AIM USB with analysis. Okay. So here it is. And if you're using a different kind of altimeter, a Raven or a Stratologger, it will have many of the same columns. And so I think this is instructive. The first column is time. And notice that it doesn't have the units, and it really ought to. So I'm going to put the units on seconds, not unexpectedly. Here's battery voltage in volts. This is a 9-volt battery, so the voltage is a little bit above 9 volts. That's good. Here's temperature in degrees Celsius. Here's altitude. MSL means mean sea level, so altitude above sea level. It also doesn't have the units, but it turns out that these are units of meters. And then here is the altitude AGL above ground level, also in meters. It turns out that I'm going to be interested in what is the altitude in feet, because remember, the altimeter 2 gave me a value in feet. So I'm going to make a new column. In fact, let me just do that right now. If I click on this column and say insert, then I can have an altitude in feet, also above ground level. And that's calculated as equals the value here of the altitude in meters times 3.281. Okay, so of course 0 goes to 0, but if I double click on this dot right there, it gives me for all of the times in question the corresponding value in feet. I'm going to actually make that a different color, make it bold, just so I can remember what data I generated and what data was original. Okay, so here's the velocity in kilometers per hour. But remember, I was interested in actually miles per hour, and I was also interested in feet per second. So I'm going to make 2 more columns. And let me just say velocity in miles per hour. And that's just equal to the velocity in kilometers per hour multiplied by 0.621. You can look up these conversion factors online. And then the velocity in feet per second, which is equal to the velocity in kilometers per hour times 0.911. Okay. And don't panic when it says some negative velocities. Basically, there's noise in the data. And so this is a rocket that's sitting around. It's not flying yet. And if I double click, it will calculate all those answers for all the times in question. And again, I'm going to color this so I can remember that those are my values. Now let's take a look at some graphs. So first of all, if I click on the time column and then I hold down Control and click on the altitude column, maybe altitude in feet, and then go to Insert, Scatter Plot, I get something that looks basically familiar. Here's an object that was on the ground at 0 altitude, and then it went up to somewhere between 3,500 and 4,000 feet, came down, and then here at about 80 seconds, this is time in seconds, it changed its descent rate, so that's when the main came out, right around 500 feet. That sounds familiar. That's what I was looking for. I'm going to click Quick Layout, choose the most basic of the layouts, and just label some things here. So for instance, I'm going to label this as time, seconds, and I'm going to label this as sensor value. And the reason is I'm going to use this same plot to look at a bunch of different sensors, and so it's not always going to be feet. And then up here, I'm going to say sensor value versus time, and then I'm going to put my initials, which is just evidence that I was the one who drew this graph. Here's something I particularly like about Excel is it allows you to use a single graph like this and look at a lot of different things very quickly. Before I do that, let me click on this axis, right click and say add major grid lines just to get some hatches every 20 seconds. In fact, just for fun, what if I add minor grid lines too? You know, I don't really care for the minor grid lines so much. I'm going to get rid of them. Ah, shoot. How do I get rid of the minor grid lines? Well, actually, let me make the minor grid lines to be 5 seconds instead of 4 seconds, and then I won't be so displeased with them. Okay, here we go. So every 5 seconds now, there's a very light line, and then every 20 seconds, there's a heavier line. If I pull this out, maybe we can see it a little bit better. And notice this flight takes just under 100 seconds. That's what I was expecting. Okay, so here's what I'm going to do. I'm going to take a quick look at some of the other sensor values. So here's a feature of Excel that I particularly like. And that is if I click on the data in the graph, it highlights in the background there what has been graphed. It shows me that I've graphed time and altitude in feet. And so if I just drag this over, I can change this into a time versus velocity in miles per hour graph, or time versus feet per second graph. In fact, let me just look at that miles per hour graph for the moment. It shows me that my velocity goes from 0 up to just over 463 miles per hour. Seems to be the peak velocity according to this sensor. And the altimeter 2 said it was 497 miles per hour. So that's close, but not quite the same number. On the other hand, when I'm coming down here, if I hover over a part of the graph, it will tell me a little bit about the data that's in that part of the graph. And so sometimes at least, here we go. So minus 39 miles per hour. And then later on, oh, here I changed from coming down faster under drogue to slower under main. And these numbers are, instead of being 39 miles an hour, it's more like 17 miles an hour. But remember, I'm curious about this value in feet per second. So let me just drag this over one more. And then here I see that I'm coming down under drogue only at approximately 55 feet per second. And then I slow down to more like 26 feet per second. So I suspect that value that was given by the altimeter 2 of 44 feet per second must have been an average of the descent under parachute for both parachutes. And notice I was under the drogue for much longer than under the main. So the average kind of favors the drogue number of 55, and the value of landing 26 feet per second, that's not considered unsafe. A little bit higher than I might have chosen, but anyway, this is all basically making sense. Here's one more thing that's very interesting. Notice that if I go back to the altitude, I see that I reach my peak altitude at about 15 seconds or so. And then I reach 500 feet at about 80 seconds. And if I were to go over here and take a look at what's happening on line A, I notice that line A spikes right at about 15 seconds. For 2 seconds, it stays on. That's the firing of line A. That's the drogue charge. And then if I look at line B, I notice that that fires at 80 seconds. So in other words, on this particular altimeter, it records what's going on in the various channels, the various lines, and I can see when the various charges went off. One of them went off at apogee, and one of them went off at 80 seconds, which was just as I was passing 500 feet on the way down, and it helped me pull out another parachute. So I'm basically happy with how this is going. I understand what has happened. I understand how fast I was going. The altimeter 2 suggested I was going a little bit faster, and maybe that's inconsistent, or maybe that's consistent, noticing that this is only updating once every 1/10 of a second. And it's possible that the altimeter 2 is able to update more quickly than that and come up with a more accurate answer. Now let me look at, so let me minimize that. Let me look at some paddle data. So a paddle is a flight computer. It's a sensor suite. It doesn't fire charges, but it has a GPS and it has pressure sensors and other things. So let me look at the paddle for Team D. Here we go. It's already in Excel format. And the paddle will have many, many more columns and a lot more data. And it runs, there will be yes, here's how fast it's running. Here's the time in seconds. Here's the time in milliseconds. And I'm going to save this as well, just to make my own copy of it. So I'm going to call this with analysis. Save. So it turns out that it's important for you to know what the various columns mean and label them well, and hopefully put units on them, at least when it's appropriate to do so. It sometimes isn't appropriate. It turns out that here, for instance, is latitude, longitude, altitude, meter, and altitude in feet, altitude in meters, maybe millimeters, but they're all zeros. That just tells me that the GPS has not yet locked. In fact, having been looking at this data a little bit already, I know that this latitude is equal to the latitude here in Minneapolis, okay, or in North Branch, is close to 45 degrees. And if I scroll down, I see that that number, make that a little bit wider, eventually becomes 45 with a whole bunch of extra digits. And so in other words, this is not latitude, this is latitude times 10 to the 7th. Not totally sure why they chose to record latitude, but if I want the latitude to be in decimal degrees, I just have to take this number and divide it by 1 with 7 zeros, 3, 4, 5, 6, 7. Okay, this is a purple column. And one thing I'll notice is that the latitude stays 0 for a while. It doesn't lock. And then when it locks, it doesn't lock right away. It kind of wanders around. In a moment, I'm going to figure out where the flight occurred. And I'm only going to focus on what happened to the latitude during that time. Here's the longitude. Let me make it longitude decimal degrees. Column. So that would be equal to this number divided by 1 with 7 zeros. 1, 2, 3, 4, 5, 6, 7. Make that a purple column. And then this happens to be feet above sea level, not above ground level. And my expectation is around here in Minnesota, most of the altitudes are about 1,000 feet above sea level. And so I believe that this is feet times 1,000. So I'm going to make feet altitude, feet above sea level equals this number divided by 1,000. I believe that's the correct conversion. We'll find out in a moment. The first thing I really want to do, actually, perhaps I could have done this even earlier, is just find out where did the flight occur. So let me graph time in seconds versus pressure right here. Here's a pressure column in kilopascals. It should be about 100 kilopascals. It's 98, so that's about what I expected. I also have pressure in atmospheres. I have pressure in PSI. And then over here, I have altitude based on this pressure. But let me just first graph the pressure straight up. So hold down the control, choose that column, insert, scatter. And here's what I notice. I notice the pressure is very, 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 very steady until the very end of the record. And then suddenly the pressure dips and then it starts to recover. So this is the flight. So that just means I want to focus on times, but my times, I want to focus on times that are more than 5,000 seconds. And in fact, let me just put some labels on here. So again, this is going to be, oh, sorry. I lost it. Try that again. Graph seconds versus pressure. Insert scatter chart. Quick layout. I'm going to call that sensor value versus time. My initials. And this is time in seconds from when it was turned on. But it was on for more than 5,000 seconds before I actually flew. And then this is sensor value. Which in this case right now is in kilopascals, but I'm going to use the same graph to look at other things. Let me focus on where the flight occurred. So if I were to double click, and instead of graphing from 0 to 6,000, let me graph from maybe 5,200 to, yeah, that was good. 5,200 to 5,400. That's great. So that shows me a level pressure and then decreasing pressure as the rocket climbs, and then diminishing or increasing pressure as the rocket starts to come back down again. That's fine. So there is the flight. The flight takes place from, add major grid lines, from about 5280. And it looks like the record stops before it reaches the ground. So this is not a complete record. This is a record of the ascent and most of, but not quite all of the descent, but not even hitting the ground and sitting on the ground afterwards. Okay, so that's worth knowing. I won't be able to get the full flight time out of this record because it doesn't go quite all the way to the landing. If I click and change this from pressure to feet, that looks kind of familiar. Basically, it shows that I started with nearly 1,000 feet above sea level, and then I went up to 4,500 feet. This is a little hard to compare to the altimeter 2 because the altimeter 2 measures above ground level, and this is above sea level. On the other hand, if the GPS worked, the GPS will also give an impression, an opinion. And in fact, I think I will stop this video after doing one more thing, and that is I'm going to look at the altitude on the GPS. So let me make an entirely new graph. And this new graph is going to actually have three things: time, and then hold down Control. And then here is the altitude from the GPS. So I'm going to grab that column, and Control is still down, and I'm going to go all the way over here to the altitude based on the pressure sensor. So now I've chosen three columns, and what it will do is it will plot the last two I chose vertically against the first one I chose horizontally. Insert, scatter. Now this looks very strange. And the reason this looks very strange is it scaled it based on the biggest numbers it saw, and it saw some really monstrous numbers as the GPS was trying to lock. I want to focus on this little blip right here. This is the actual flight. So remember, what I'd like to do is only look at 5,200 up to maybe 5,400. Fine. And then if I click on the vertical axis, let me just look at altitudes from 0 up to perhaps 5,000. There we go. So here I have in two different colors. One of them is based on the pressure, the altitude based on pressure, and one of them is the altitude based on GPS. And notice they both are level, and then they both go up, and then they both come back, start to come back down. But notice they're offset. What this is trying to tell me is that these two devices did not exactly agree on what happened. Here's something I might want to do. Click on, double click on that color and go over here to marker options, built-in size. I can make those dots smaller. It only made one of the dots smaller. I wanted to make all the dots smaller. Let's see if I can get all those. Try it again. Well, this is not going quite the way I wanted it to. Sometimes when I click on the data in the graph, it grabs one point, and sometimes it grabs all the points. I was trying to grab all the points and make them all smaller, but not today, apparently. Okay, I can still tell that feet, FT, that's this red-orange color, that's the pressure sensor value, and it looks like that indicates the flight starting maybe about 5 seconds earlier than the GPS. GPS is the blue one. That just tells me that the GPS more or less stayed locked. That's good. But it took it a while to notice things were happening. In other words, the GPS processes things, and it takes a while for the GPS to process stuff. It's much slower, apparently, than the pressure sensor. Similarly, I noticed the GPS numbers don't go as high. Basically, the pressure sensor values go up to 5,300 approximately, and the GPS values only go up to, if I can click on the blue and not on the orange, a little bit difficult. It would have been easier if I'd been able to make the dots smaller. But I can see here that the blue line, the blue curve is lower down than the other one, suggesting that the GPS is not only slower, but since it's slower, it doesn't actually notice how high I got because I was already on the way back down again before it got its act together. That's fine. That's neither here nor there. Like I said, it's a little hard to compare these numbers to the altimeter 2, and the reason is the altimeter 2 is values above ground level, and these are all values above sea level. But if you were just to subtract off the distance between the ground and the sea level, in other words, what was the original number? And the answer is it's somewhere here, close to 1,000. Then instead of having numbers that are above 4,500, you'd have numbers that are somewhat below 4,000, and that might be more consistent with what the altimeter 2 said and what the AIM extra altimeter device said. Okay, there's lots of other stuff here. So in this particular thing, it has gyro values, it has accelerometer values. It has magnetometer values. It might be interesting to try and figure out which of these X, Y, or Z is actually the vertical axis, and that shouldn't be too hard to figure out. In fact, let me just do that right now for fun. Yes, I have two graphs on top of each other. Let me go back to this graph. And I'm going to take a look at the accelerometer values that is labeled Y. And I see things sort of bouncing around between positive 1.5 and negative 1.5. And then I go to accelerometer values that are labeled X, and I notice that things have a huge spike at this time. That was the launch time, down to possibly positive 3 and minus 15. So clearly this is the axis that's in the direction of flight. And then this third one is also just bouncing around. Wow, this reminds me though, that there's another sensor that I'm particularly interested in looking at. First of all, let me go back and remind myself on these units, the ascent is from about 5280 to 5300 or so. Okay. The reason I'm interested in the ascent is I want to go over here and take a quick look at my photoresistor. There it is. So right now I'm plotting the values of the photoresistor. I better zoom in a little bit because I'm not seeing a lot of variation in the photoresistor. Let me change this to be plotting from maybe 900 to 1100 or so. Okay. So remember, this is where the launch occurred. And so prior to launch, the levels of the photoresistor were pretty steady. And then once the thing was flying, they started to vary. And that was because the thing started to spin. If I focus just on this part, so I'm going to zoom in right on this part. I'm going to go to maybe 5280 just before launch to 5300, which is basically just after it reaches the peak. So 5280 to 5300. Ooh, this is nice. What this is showing me is the thing is going up and down and up and down and up and down. Let me even zoom in a bit more. 5285 to 5290. 5285. 5290. So here I see that it was up and then it was down and then it was up and then it was down. Basically, this is sort of not exactly sinusoidal, but it's definitely varying. And this variation indicates the fact that it's spinning. Here's one thing I might want to do just for fun. Let me change by double clicking on this, by right clicking on this. Let me change the chart type from a scatter plot to a scatter plot with the dots connected. And then I can see more easily this variation. So up, down, up, down, up, down, up, down. And this indicates rotation. You can figure out that it's rotating. If this is 5286 seconds, 5287 seconds, it looks like over a course of 1 second, it went up. It went from down to up to down to up. So it's rotating about twice a second or so. And if you had some other thing like a video, you might be able to confirm that this is happening. Similarly, you might be able to figure this out by looking at gyroscope data. But this is very simplistic light data, looking at light coming in through a window in the AFBEG. But I had to zoom in a lot. I had to zoom in a lot to spot this. And I also wanted to focus just on the ascent. And the reason is if you look at the descent, things tend to be very chaotic as the thing is coming down under parachute and it does not spin in a regular manner. But here on ascent, it seems like it's spinning and it maybe is even slowing down. So here it's up, down, 2 or 2.5 times a second. And by the time I get over to here, close to the peak, It's spinning, but it's only going up and down once per second. In other words, it's spinning, but it's slowing down its spin rate. So all this information is available, not from the AIM USB or the Raven device, but from the paddle device, the extra sensor suite that we put on board. Okay, there you have it. Just a little bit about data analysis from a high-power rocket flight.